Okay, year 12, this is the second part of my video commenting on young Slit's diffraction. The first little bit you need to know about is what is meant by coherent sources. And basically, these are two sources like you've got in young Slits, where you have source 1, S1 and S2. And they must have, the sources must be, a coherent source, two different ones, have the same phase, either phase linked or phase locked together, and the same frequency, and that's very, very important. And this comes in here is why you need them in young Slits. So in young Slits, where you've got, I can get my little pen here, you've got a source S1 and you've got a source S2. These have got to be in phase, coherent sources, or phase locked. And the reason why is, otherwise you don't get interference pattern when you've got your bright, dark, bright, dark, bright, dark all the way down through here. Now, if you've got two lamps here and they're emitting light coming out, believe it or not, well, light is not like, it basically, it pulses on and off a little bit because you're producing photons quite erratically. Therefore, if you've got two lights here, they're not going to be coherent sources, they're not going to be phase linked, they're not going to have the same frequency. Therefore, what you've got to do is you've got to pass them through a single slit first of all, which is here. Then when the light comes out, it makes sure that S1 and S2 are coherent sources. Amazingly, Young's did this way back in 17, God knows what, using a candle. You'd have electric light bulbs then. If you're using a laser, and we will be using a laser in the lab when we do this experiment, you don't need this bit here. The reason why you don't need it is because laser light is monochromatic. Number one, it's got light on one wavelength, but also it always produces a coherent light source. It's different to a lamp. Therefore, what you find then is you can literally get rid of this bit, literally put a laser light on S1 and S2, and you get a nice interference pattern. Now, what we're going to start going through now is why, when you basically shine light through, going through a laser, going through young Slits, you can see the dark, bright through here, and the fringe spacing starting to appear. We can see a black splodge here and a black splodge here. And that's the bit I want to explain really. This video is quite tricky. So it all comes into, first of all, diffraction. Now, in diffraction, you do get an interference pattern. To help you understand why you get an interference pattern, going back here, you might remember I explained diffraction in the first part of this video, is by having different sources here, S1, S2, S1, S2 here. So as the light comes through, these are acting like different sources to create the bending, the diffraction of the waves as they go through. But these different sources here are going to interfere. Hence, when you, that's the wrong one, get back to here, you do see interference pattern in diffraction. Therefore, you get your bright here, your dark, your bright, your dark. Okay, we get dark and bright fringes. But the important part to see here is this one, its width is going to be twice of those. Therefore, this is twice than that one, all the ones going out. Now, to go with that, you've got a formula. And don't worry, these are on your formula sheet, but they're tricky. Now, I think in your book, you've got this as a big W. They call that a small w. Now, this is for Young's, is the width separation. Where lambda is your wavelength, D is the distance from S1, S2, the two slits to the screen, and S is going to be the slit separation. Now, for diffraction, this is basically the width of the central fringe. Lambda, again, is the wavelength. D is a distance from the single slit to the screen. A is now the width of the single slit. The 2 is here to represent the 2 because that is twice the width of those, and that is why you've got a 2. If you take this equation and rubbing out here now, if you want the width of the ones away from the center one, you don't use that 2. They are in your formula book, but you do need to see them working. Now, to go with that, like I've done before, is I can show you this happening in simulation. Therefore, if D starts to go up, W should increase, i.e. the width of the central fringe. Now to show you that, oh dear, and I've lost my simulation, going back over here, is I can go back to this one, which is the simulation I showed you before, and hopefully I'm going to find it, if it kills me. Here we go. Bing. What you've got here is, I showed this beforehand of whether you had young slits. If I now go to a single slit diffraction, here you've got the central fringe. This is twice the width of those here. Therefore it goes bright, dark, bright, dark. Now in theory, what I just said, going back to the formula, can't which way we've got which one I actually changed now. If I made D bigger, the central fringe should get wider. So going back to the simulation, I'm now going to increase D, and look, it's got wider. If I make D smaller, W gets smaller. Then going back to the formula we got here, now again, if I make the wavelength is going to be bigger, that also should get bigger. Going back to my simulation, wavelength, I'm going to increase it up to red. You see again, the width of the central fringe has got bigger as well. The formula's working. Then going back here again, choosing a different color pen. If I make A bigger, in theory, W, the width of the central fringe should go down. Therefore, going back to my simulation here, if I make N here, make that bigger, you see now the W's got a lot smaller. So that is the single slit diffraction pattern. Now that's important to explain the next stage, because you've got this in your book. That's a little bit confusing. Do not panic. You might have got, I'll get this 100% now, but when you come back, we'll do it again. Eventually it starts to stick. Now, what you've got here, the dotted line here going out through here is what you'd see in Young's interference pattern, i.e. Young's fringes. Bright, dark, bright, dark. But you don't get that, because what you've got to appreciate is, zipping back here, when you're doing Young's experiment, doesn't the light first of all go through a single slit, have a diffraction pattern, then you've got the interference of S1 and S2. In other words, you've got a diffraction single slit interference pattern overlapping the interference pattern. In other words, going back here, what this is trying to show you is the blue is the single slit diffraction pattern. We call it an envelope. In other words, it goes up and down, where this is going to be 2W and that's going to be W. Now, if you didn't have the single slit diffraction envelope, Young slit will look like this. So in other words, here is going to be your first little fringe going out. It cuts off and it comes down to here because the single slit diffraction envelope cuts it off. Here, it brings it right down to 0. In theory, if you had an interference pattern that was going up here, you wouldn't see it at all because it'd be cut off by the single slit diffraction one. This one gets cut off and it's brought down here. So in other words, your Young's slit interference patterns inside the diffraction single slit envelope. To show it on my simulation here you've got your Young slits. Now Young slits, you've got blue light going through, you've got source 1 S2, you can see bright, dark, but the intensity goes up and down, where it's bright in the center here, because here you have got your single slit envelope. Therefore, the line going up here over here, there's your single slit, therefore your Young's inside. Now, if I make this slit width much, much smaller, in theory, the central fringe becomes narrower, which it has done. So now, if you make the W much narrower, it's cut off here and here and here. So you don't now see all the bright, dark, In other words, it looks bright here, you've got a dark splodge here, and you've got a dark splodge here. If I then take it back again to about midway, you can see it changing as I'm making the single slit width bigger and bigger and bigger and bigger. So if I go over here, you can practically see the whole lot now. So you make S very, very small. So what you've got to be able to do, and the tricky part going here, is you've got to be able to see how this pattern forms. Therefore, you do need to use both these equations at the same time, and these do come up multiple choice. They're very tricky, and you may need to see it 2 or 3 times to get your head around it, but eventually you do start to see it. So don't panic. If you found that hard, we will go through it again when you come back into college. Don't panic. Anyway, hope you got a bit of an idea of how you get the Young's fringes inside the single slit diffraction envelope.